antennas and their equivalent circuit analysis. And then we'll start with some general principles from chapter 3. And in fact, chapter 3, it's all about the mathematical apparatus which is used, which means that you can often refer to this chapter on the possible steps that can be used regarding the mathematical apparatus, how we can define or how we can find the electric field from the sources. So if we're given a couple of sources where these can be, for example, currents or even magnetization or pulsing charge, we may want to find from these sources the relevant fields. This would be regarding chapter 3, but the tools that will be presented in chapter 3 will be used during the whole semester. But before we go to that, let's have a look at a couple of examples. Okay, let's start somewhere here. So let's assume that we have an antenna which has a radiation resistance. This is a radiation resistance equal to 48 ohms, loss resistance 2 ohms, so we have a loss resistance of 2 ohms, reactance of 50 ohms, so we have a reactance of 50 ohms, and this is connected with a generator So this antenna is connected to a generator which has a voltage equal to 10 volt, and the impedance of the generator, so it has this voltage, it has also this is the impedance of the generator. This is equal to 50 ohm, and we are using also a transmission line So we have the antenna with these parameters is connected to a generator through a transmission line which has a characteristic impedance of 100 ohms. So ZPL is equal to 100 ohms. So in fact, the impedance of the generators often it is in this range, something between 50 ohms to 75 ohms. And what happens is that often in old antennas, or let's say the simplest possible antennas, the impedance of those it is relatively small, and we know that which means that it would be a huge mismatch between the old type of the used antenna and the traditionally used generators that have an impedance of around 50 ohms. Whenever these two are connected, a lot of reflection happens, so there is a very low reflection efficiency, so we lose some information. So you can try to memorize this. Something between 50 ohms and 75 ohms would be normally the impedance of a generator. Also, many multimeters or oscilloscopes that you can find here in the lab, they have two settings of the internal impedance. It might depend on the product, but sometimes they have a 50 ohm and sometimes 1 mega ohm impedance for the input signals. So whenever you are reading a voltage into a digital oscilloscope, you may have to switch, or at least to test the two possible different impedances by selecting it. Now let's see the problem again. We have this antenna, it's connected to the generator, we have this transmission line, and now the first question is, let's try to see how this circuit appears, or what is the circuit equivalent. So that's the first question. And here, regarding the circuit, probably we can draw this one here. So we have the generator. It generates 10 volts. For sure, this 10 volts is not going to be DC. It has to be AC. So we have to use the relevant notation. But here we have a resistance of 50. Then we can use a transmission line, which is, so this is the, so I just want to denote here that this is the specific transmission line, which has, and let's have a look, the transmission line, it has an impedance of 100 ohm. So this region, or at least when we see this region, we just want to denote that whenever the signal is going from this segment to the other segment, is going to be phased with an impedance of 100 ohm. This is the transmission line, and then we will have on the other side, we'll have the connection of the transmission line with the third component of the whole construct, which is the antenna. And this antenna, it has we can denote here that the impedance of the antenna is equal to 50 plus G50. So because we said that the reactance of the antenna, it was equal to 50. Now this is the equivalent circuit that we can draw here, and let's see again. Now, okay, so the next question can be the following. What is the power supplied by the generator? So P So, what is the power supplied by the generator? And the power supplied by the generator is going to be equal to, or this one will be equal to 1/2 times the real part between the voltage of the generator times the current of the generator. So this would be the power supplied. And another question can be, what is the power radiated by the antenna? So what is the power radiated by the antenna? And the power radiated by the antenna is going, we can, so the power of the antenna itself, we can write this one as 1/2 the current of the generator square times the real part of the impedance and so this is the whole power, and we have to multiply this one by the ECE, by the efficiency which we denoted as the ECD. So this will be the power that will be present in the antenna, but we have to account also for the possible losses that can happen. And now let's move again. Let's have a look. So firstly, we can try to we have to find the current And this current, it has to be equal to the potential divided by the whole resistance, and the whole resistance here is going to be equal to 150. Let's see. So we have here the impedance. We have here 150, so we have to. This is the current that will flow beyond the generator, and here we have to add the resistance or the impedance of the transmission line together with the resistance of the antenna. And here, let's see here for a moment, we have 150 plus G50. The generator, it has this impedance. I cannot wait a second. So here we have the total loss. So we have the antenna. It is 50. So we have the radiation loss. We have the radiation resistance, the loss resistance. So those two are purely resistances with no phase difference at all. That's why we get that 50. And then regarding the current that we develop here, this is equal to plus J 100. This is 150 plus J 100. And here in this calculation, if the amplitude that we are going to obtain here is that we have to find what is the magnitude between, or the norm of these numbers. So 150 plus 100, the magnitude of this impedance, this is going to be something around. So 100 squared, this is 10,000. Someone can calculate this one? So if we have 150 times 150 is 22,000. Okay. Then we have to add here 100, 32,500. Then the square root of 32,000, square root of 32,500. This is around 180. Okay, 0.3. So we're just trying to identify the magnitude of this term. So we get 180.3, and then we have to include also an angle which is related to. So we have a reactance of the real part.
Sorry.
Yes.
Christina wrote something in the chat about the current. Shouldn't it be 200 plus 50J?
Was it 200 plus
the resistance?
No, here in this resistance, let me think for a moment. Let's see this one. Plus 50J. Let's think for a moment. 150 plus 50. Oh, let's think for a moment. So we have the resistance or the impedance, which comes from the IG. This is the IG squared Z in. This is 100 squared divided by, let me think for a moment, 50 plus 50G. Actually, in this case, I believe this is 150 plus 50. Plus 50. Wait a second. The current will be supplied over. Actually, I'd rather consider this one. Let's notice once again. So we have the reactance here. We have a clear reactance of 50, and the transmission line has 100. And then, wait a second. This would be 150 plus 50. I'd rather do this one. Okay, plus 50. This would be plus 50 because this would be the resistance which is seen beyond the generator, okay? And then actually I said plus, I think plus 50 is better because this is the reactance that will be observed by the rest of the generator. That's how I think it's better this way, but we have to adapt the. Okay. I think this is better. But then we have to adjust the numbers. When we say adjust the numbers, this value we have to correct this one, and then we have here 150. So we need to identify this angle theta, assuming that the resistance is 50 and 150. This is going to be 150. Sorry, plus 50 squared. So in this case, this will be 150 times 150. This is the same. Wait a second. This is the same plus. This is 25,000. 25,000. The square root of 25,000. This is 158. So we get here 158, and then .06. Okay, so this will be the. Let's think for a moment. So that will be the magnitude, and we have to include also the phase angle, which has to appear, which will be the phase angle between the voltage and the current. And now we need also to include the Z squared. Here we have voltage squared divided by the resistance. Okay, so here G. Wait a second. This is G times 10. In fact, This is the power supplied. Sorry, actually, regarding the power supply here, this is going to be approximately. So let's do this one. This will be 1/2 times 10, which would be the potential, the AC voltage that we have here, and we multiply this one by the IG. And we have to include the real part. Since this is the complex conjugate, we have to include here the cosine of an angle, which is going to be equal to approximately arc tangent of 50 divided by 150. Okay, so this will be the power supplied by the generator. Okay, so this number. This is what we need for now. And regarding the power radiated by the antenna, we have to use the expression. Wait a second. Square times 100. The ECD. Actually, the formula, can somebody look? Let me try to find this. I don't have the, can somebody find the formula for the effectivity? We have this beautiful 2-page ECD. I don't have here for the moment. Can you look from the book? What is the formula for the ECD? It is a relationship between the, okay, I found it. This is radiating resistance divided by RR, yes, plus RL. Now, regarding the equation, you can just look at the formula sheet in pages 101 and 102. And here we have this is going to be something like simply 48 divided by 48 plus 2. So the numbers that we can get from here, this is going to be 48 divided by 50. Okay, so we have the ECD. Now we have to multiply we have the IG square. I mean, that value we can easily identify, but we need now to. This is real part of Z input impedance. This is. Okay. So here we get the 0.06 square, the real part of the input Zin. Now Zin, if we look at the relations that we have in the 50 plus square, this would be the Z in. And now we are at this part. We have to consider only the real part of the Z in. And the real part of the Z in so now this is, we're looking for the real part of the Z in, and the real part of Z in is just the magnitude. So this row here, this is going to be the magnitude of this complex number, or let's remind that A plus JB, this is equal to some amplitude rho times cosine theta plus J sine theta. And if we're looking for the real part, it would be this one. And in fact, this is what we obtain. And the real part. Okay, then we have 1/2 times the real part of the Z in. In fact, in this case, the magnitude of this Z in is equal to 100 times square root of 2. So a few terms will cancel out here, in fact, because here we'll have that 100 times square root of 2. This is the magnitude of a complex number that has, so that is a minus, but the magnitude is going to be the same. So this amplitude here is going to be this one, but if we multiply with the cosine of 45, that's the angle that we have here. The cosine of 45 is 1 over the square root of 2. And this would be simply equal to 100. So here, then we just here multiply here by 100. This would be the real part of the Z in, times the radiation efficiency, which is 0.96. And here we can calculate the results. Sorry. So this is, it's going to be a number. (0.96) times 0.06 times 0.06 divided by 2 times 100, 0.17. So this will be approximately the power radiated by the antenna. Okay. Okay, so this was an example when we covered the similarities, or at least the circuit equivalent of the antennas with respect to the circuit equivalent of the complete antenna construct. Okay, so next we want to, as we said before, we want to go over some concepts that are general, or let's say not only concepts. It's really, this chapter 3 is just kind of a repetition of several aspects that we have done before regarding the mathematical apparatus. One thing that you might need some review, it would be the part, or the complex calculus part. With complex calculus part, we are going to see when this comes up. So the general perspective of what this chapter 3 is offering is the following. So normally we are given the sources of the fields, electric field and the magnetic field, the intensities in this case, which would be the E and H, and we can often use only the first path, which would be integrating. So we find these from the equations, from Maxwell's equations. So integrating those equations, we can find the E and the H. Now we can use another approach, which would be the approach of, from the sources, we can find the vector potentials, the A and the F. And in this case, after we find the vector potentials, we can we can differentiate, and we can find the electric field and the magnetic field intensity. Now, we would prefer to use the second path. It looks a longer path, but the integration to find the A and the F, they are relatively simpler, and differentiating expressions, it is always simpler, or much simpler than integrating expressions. So what we want to say here is that we said that we want to find the fields, but we're going to introduce these auxiliary functions, which are the vector potentials. And these vector potentials, you have seen this before, especially the A, which is a magnetic vector potential. And now here we have also the F, which is an electric vector potential. And from these two, so after we introduce these potentials, we can determine the E and the H, as we said. So these are the topics that we can go over, and the first two or three, they are mostly related to a set of equations which that we can use. The rest of the chapter, especially the duality theorem and reciprocity and reaction theorems, it's just some conceptual approaches where one can use a similarity between the equations provided to derive the other. So there is a strong similarity between different pairs of equations. We talked about these two possible paths that we can use for the fields. Now, here we have that actually these terms that in this textbook we have this Hertz potential, or these new notations, which is this Greek letter. The first one for E would be analogous to the A, and the Greek letter H, this is analogous to another vector field F. And the function relation between these, it's only a proportionality constant, which is a function of the frequency and the parameters of the medium. And when we talk about the parameters of the medium, we're talking about the permittivity and the permeability. Now, when we are going to analyze the sources and the fields that they do create at a certain distance, traditionally we have two approaches. One of them, not approaches, but we have two ways to write down the equations. One would be one where the source is located at the origin. The other approach is when the source is not located at the origin, and the point where we want to conduct a measurement, it is going to be described by a vector r, which is going to be equal to the r, small r minus small r prime. So it would be this vector, which is from the origin to the point of observation, minus the vector r prime, which is from the origin to the point where the source is. And the difference between these two, it is simply the vector r. Now, the vector potential that we can find for an electric current source J, we can use these expressions that we see here. So we know that the very first expression is a postulate. The divergence of B is equal to 0. So since the divergence of B is equal to 0, based on the vector properties, we know that if this is true, then that means that B can be written as a curl of another vector potential A, and we call this one magnetic vector potential. And this BA, is related as a function of the properties of the medium, which would be the mu. It will be related as shown here, where B, it would be equal to mu times H, and this would be again equal to the curl of A, and we can simply get the relationship which states that the magnetic field intensity is equal to the curl of A divided by the permeability. Now, if we substitute this in the into the Maxwell's curl equation, actually in this one here, we obtain this an expression where the created electric field, because how to say, the H itself, it is related to a curl of to a relationship of curl of A, and what we can observe is actually we're going to get this term which is down here, and from this relation we just can, as a final result, we can just notice that we can rewrite the electric field intensity as a derivative of, or at least as a product, both from a scalar potential, which is the phi E, where this phi E, it is the gradient of a scalar function, minus the j omega A. And now we know that this j omega is going to appear whenever we have a time derivative of the Maxwell's equation. So this j omega, it will be the phasor notation or the phasor representative of the original Maxwell equations. So in principle, we are, so the essential element that we see here is in fact the bottom equation, which just states that actually it's also written at the bottom. So the scalar function phi E, it can represent any arbitrary electric scalar potential, which is a function of the position. And so we know that the E is always equal to the minus the gradient of a scalar potential. But at the same time, when we are not in magnetostatics or electrostatics, we have to include also this other term, which means that because of the coupling of the electric field with the magnetic field intensity, we're going to have the modification of the EA. Now, continuing from the previous slide, we can actually finally obtain an equation for the vector potential A. So all these manipulations of the vector properties that we see in these two slides, they are just to be able to see how we can obtain the vector A. Wait a second, sorry. Why can't I change this one? Okay, so in this, I just wanted to make some extra notes here on the screen. So all these manipulations, we're just trying to come up with a differential equation whose solution would be equal to A, and it would be a function of the current density J. Okay, so let's not forget, this is slide 8. We're trying to do whatever slide number 4 is telling us, that it is from the expressions that we can write the E and the H as a function of J. We are trying to modify them somehow, not to find E and H immediately, but we want to construct a differential equation whose solution is going to be A. And this differential equation is written here, only that in this equation, or in this equation which is provided at the bottom of this slide, which is the Laplacian of the A plus k square A, and in principle the Laplacian of A, it is the del square operator. So the del operator dot del operator, we get the Laplacian square, which in Cartesian coordinate system, it is simply equal to the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. That would be the first term here. Then plus the second term, it simply is the second derivative of the vector potential with respect to time, dividing also by the speed of light in the respective medium. So that's where we get this differential equation. This differential equation is a non-homogeneous. I was trying to remember the correct term. So this is a non-homogeneous differential equation where we have to include here a J, or the current density, which is the source. Okay, so let's move again here. sorry, this was the A, this is the 9th. So we can include also Lorentz condition, and this Lorentz condition, what it is in principle reporting, is just it's one condition where with which we can simplify the wave equation of the vector A. So finally, we get this vector A, where we see that Laplacian of A plus k square A is equal to minus mu times the current density. Okay, so this is the wave equation. Now, these equations that we see so far, they were the potentials that we can calculate using the electric current source, but now we can have also a magnetic current source, which is to some degree, the magnetic current source is not something which can be experimentally measured easily. The J, we are more comfortable. But here, if we follow, so the major approach is that, again, similar to this wave equation of the vector potential A, which will be described as a function of minus mu minus the permeability times the J, a similar vector potential, we can obtain it also from the magnetic current sources. And the final result is going to be this differential equation here at the bottom of this slide. Now, if we try to solve these differential equations that we were provided, in principle, the A and A can also be written in this form, which is shown here. In fact, this expression of the A, you have done this one when you took the electromagnetic field theory, where we used to integrate, we used to find the A or different components of A from the volume integral of the current densities. So this current density is a vector quantity, which can be described as Jx, Jy, and Jz. Each one of these components is going to produce an Ax, Ay, and Az, because they are both vectors. Now, similarly, we can also have J's, which are not in Cartesian coordinate systems, but they can have projections along the spherical and the cylindrical coordinate systems. But overall, that means that actually both these integrals that we see here, and by the way, why can't I? I have to draw something here on the PowerPoint, but I'm not sure why I cannot. Okay. Oh, no. Anyway, I have no idea why I cannot. I want to draw some errors or to show us. Anyway, so I'll try to figure out this later. So in principle, this is how we'll try to find the A, which it was this trick that was defined in chapter 4, which is kind of reporting that it is better if we find the A and the F initially because of the current density and the magnetic current density. And from these expressions, now this is a summary of what we saw in the previous slides. The summary is just, it tries to find what is A whenever the current density is different from 0 and the magnetic current density is equal to 0, where M is 0. And we get equation 3.14. The solution of 3.14, it is equation 3.27, which we see here. And now, once we find A, which we find this one using the equation 3.27, which is, as we said, previous information that we got in electromagnetic field theory, we can find the H using this other equation, because the curl of A divided by the permeability will give H. And now, given this A, we can insert in equation 3.15, which is given here. We can find the E. So this is, so apparently we have to find The equation is equation in green. The solution for A of this equation is the integral, which is reported here in red. And then in blue, we find the relevant field intensities. Now, there is another approach actually, which where we can give the H, and we can try to find what is the E using this equation at the bottom. But if we want to find the electric field using this equation, which is related through the curl of H, we have to consider the current density equal to 0. Now, this is another summary as similar to this set of equations. So here we are considering a magnetic current density is different from 0, and a normal current equal to 0. So J is 0, M is different from 0, and in these conditions, the vector potential F will be a solution of the differential equation, which is shown here in green, which is equation 3.25. And if once we find the F, we can, and this F can be found using the equation in red. And once we find the F, we can use the curl of F to find the electric field intensity. And we can use also the divergence of F and the gradient of F to find the H. Or we can also try to identify the electric field if we are given the HF by using this equation 3.A, but assuming that M is equal to 0. So again, this is again kind of a summary of what we have seen. So the equations are in green. The solutions of these differential equations are in red. We find the A and F, and the current density. It has the units which are shown here in this slide. So it has units ampere per meter, and the M, it has units of volt per meter. These are the A and the E. Now all the rest is just different properties. When we say properties or different expressions which relate these components. In fact, all of these, the possible exercises to practice the knowledge that we learn in chapter 3, it is spread out over the whole textbook, because the rest of the textbook is all about calculating the electric field intensities and the magnetic field intensities from the sources. So a lot of applications, or at least yes, knowledge applying these equations, we have the chance to go them over during the whole semester. Let's move a little further. So now these equations that we see here, actually the representation of these, we'll see this one pretty soon in chapter 4. So here we have this expression for A and for the F. We can analyze these forces in the near field regime and also in the far field regime. So there are some approximations which are relevant to include. For example, in the far field, the expression of A, it can be described by this expression, which is following the approximate sign. So wait a second. So once we are in the far field regime, the integral, it will be independent of the distance, okay? Because so for this reason, the e to the power minus jkr, this can move out of the integral completely. And one thing that we should notice here is that the first exponential term, which is e to the power minus jkr, it is just denoting a wave which is propagating along the increasing values of r, but that one is modified by a factor which is 1 over r. This is the... And other aspects that we may consider is that the A, it is in the far field regime, we like to express the currents, not only the vector potentials, but also the field intensities. We like to represent them in terms of the spherical coordinate systems, because as we as we are going to see for antennas, and we like these units also for the fact that we can have two types of powers in an antenna. One power that can oscillate, or that we call it reactive power, and one other power which is the radiating power. So radiating power is the power that is we can find it also in the far field regime, but the reactive power is a power which is present only in the near field regime or very close to the antenna. And this reactive power, it is a product of the components which are orthogonal with respect to the direction of the propagation of the wave. So that's also one reason why we may like to use these components, because whichever way we are getting further away from the antenna, we are often going to have electric field and magnetic field components which may resemble a TEM mode, a transverse electromagnetic field mode. Now let's move again here. So this is the far field regime. This is the similar analysis regarding the F. But let's see actually how much information we can add here. For example, we observe here that as if we're trying to find the field vector, let's call it the F vector. So if we try to see this equation at the middle of the slide, this is simply apparently it's a half wavelength antenna. So it's going to be an antenna which is where we have an oscillating current, and this integral of the oscillating current we are integrating over the body or over the structure of the antenna. So this could be our antenna. It can be a short component, and the current is oscillating along this conductive layer or conductive material. And as we can see here, also the integral, it is simply it is integrated from minus L/2 to L/2, and we are going to the product, which is K dot R. We receive, or we see that we will be left with the EJKZ times cosine theta. Now, when we see an example, we can talk more in detail regarding this. Actually, I missed this part. I just went back 2 slides, and similarly, apparently here we are also looking at the solution for the A field vector, which is created by a linear antenna, and we are integrating over the current, which in this case, since the current is flowing into a component of the antenna, which is going to look like this. This is why we are integrating over dz, and apparently the antenna is also pointing along the z-axis. Now, theorems. Now, this part we can skip this a little faster, because these theorems, they just represent the similarity between a whole pair of different quantities. For example, when 2 quantity equations that describe the behavior of 2 different variables, if they have the same mathematical form, the solutions will also be identical. The variables in the 2 equations that occupy identical positions are known as dual quantities. Now, this idea of duality, we have mentioned this one, at least you have seen this one, also in electromagnetic field theory, where we have reported that because the solution of one differential equation has a certain form, the solution, it always be similar to those. And actually, sorry, I'm just going back. For example, in equation 3.27 and 3.28, this logic or this approach, it's mentioned even in earlier stages before you can take antennas, where we have said simply that if you want to find specific components of the vector A, if we want to find the AR, which could be now A in the direction of the propagation, we have to use the JR, okay? And this duality is also used for A theta, where A theta is going to be now a direction which is perpendicular to the direction of R when R is increasing. Now, to find A theta, we have to use J theta. So this principle of duality, we always use it. Actually, for vector quantities, it's also very, it has much more intuition into it. of why that should be true. So now let's go back to this duality expression. So here, this is what duality is all about. So we have here that the curl of E, we see the first equation, it is equal to the minus j omega permeability times H. Now the curl of H is going to be also equal to the j omega permittivity times E. So this is the duality that we want to talk about. So if we look at the equation, the fourth equation, you can see that the vector potential A, it can be written as a source using the J as a source, and the same thing can also be said for the vector potential F, which will have as a source the vector M. Now this is again duality, which simply, and when we say duality, this is also something regarding the equivalent expression from the magnetostatics and the electrostatics. So even in those expressions, we can see, in fact, that permittivity and permeability, they are equivalent. We can use the equivalent principle. We have also that the permeability in the electric sources, it is equivalent to the permittivity in the magnetic sources. K, it is the same, and the intrinsic impedance in one domain, it is intrinsic impedance. On the other domain, it is inverse intrinsic impedance. This duality, I remember that when we did together electromagnetic field theory, we used to have some expressions. Right now, I've not memorized them, but I'm trying to remember. So the potential, which can be created because of a dipole, I really forget this, in fact, but I think that it used to be 1 over epsilon 0 relating the electric dipole dot AR. This is something, and we have another vector which can be as a source of the magnetic moment. So we have the magnetic moment here, dot AR, and here we have mu0, and similar to this, and actually this dipole moment P, this is equal to QD, and the magnetic moment small m, this is equal to I times area. So this is what the small magnetization vector was. So whenever we write the set of equations for the potential, which could be as a result of the dipole, so if we have a single, we know the potential can be if you have a single charge, if we have two charges but at a certain distance, but which are very close together, we have another expression for potential. And by the way, this potential, for sure, it has to have 1 over r squared, and this is, we might expect also another term, 1 over r squared, because point charges, the potential changes as 1 over r as we're getting far away from it, but dipoles have a different potential dependency on the radius, which would be not 1 over r, but 1 over r squared. Now, we can continue with chapter 4, but I really wanted to take some notes here on the slides, but I cannot for the moment. Okay. I cannot even save as this thing. No. Okay. Okay, let's continue then. So now, as you said, actually, chapter 3, it was relatively short. Now we want to talk about, we want to pass to chapter 4, where we are going to discuss the linear wire antennas as a first type of antenna to go over. And we'll see that the first type of antenna that we're going to analyze is an infinitesimal dipole. So infinitesimal dipole, it's a linear wire where the length is much smaller than the wavelength of the wave that is propagated by this antenna. Now, in order to visualize this one, we often position this one symmetrically at the origin of the coordinate system. We orient it along the z-axis, and now they can also they are used for as units to construct more complex antenna systems. And as we said, the wire is very small, so the length of the antenna is much smaller than the wavelength, which means that if we are, so gigahertz communication, it's something between 30 centimeters to 1 meter. But now, if we want to have a larger wavelength, then that means that we have, so if we want a larger wavelength, we want to have a shorter, smaller frequency, which means that not in gigahertz, but something in the hundreds of megahertz can produce, makes possible to have an infinitesimally small linear dipole, infinitesimal dipole. Now, when we analyze the infinitesimally small dipole, we use this geometry. As we said, actually, the dipole, we orient it along the z-axis, and we assume that the wave is propagating along the direction r, where r is measured as a function of, the r is oriented at an angle theta with respect to the z-axis. Now, we don't see, because of the geometry, we are not going to expect a dependency of the different quantities as a function of the angle phi. So this angle phi, which is shown on the xy plane, is not going to have any effect, because it doesn't matter if you are at the front of the dipole or the back of the dipole, to the right or to the left of the dipole. They are all equivalent. And now, in the electric field orientation that we are going to analyze, we expect the electric field to have a component along the ER, E theta, and the E phi. This is all expected. And now, if we have this current I, which is going to be on the infinitesimally small dipole, the vector A can be found using this expression. So we'll try to use this approach of finding first the A, and then from A finding the E and the H. Now, the current in this infinitesimally small dipole, we just denote it as shown in here. So the current is going to be AZ pointing the direction times the I0. Now, this I, of course, it's not going to be a DC current. It's going to be an alternating current for sure, and rather than just being an alternating current, we're assuming that it is a harmonic current, which means that it's going to change as a function of like a sine or a cosine. So, for example, we see here that the real part of the current in the phasor notation is simply going to be I0 times cosine omega t, because we're looking for the real part. Now, the vector potential that we are going to find, we said that the A is going to be expressed as shown in here. This is the general expression for A. Okay, so we can have the near field approximation for this expression for A. We can have also the far field approximation for the vector A, and R that we can analyze here is given by this expression. But in fact, what this really means, this means if we have this x minus x prime, we said before that this x prime would be the location of the charge. So if x prime, y prime, and z prime are equal to 0, this is what we get for R, okay? Because we can simplify the expressions much easier if the source is at the origin. Now let's move ahead here. We can find the A given this integral here, and since we are going to integrate along the Z, we have, wait a second. So first of all, actually, so these equations, it is imperative, or it is relatively easy to assume that the vector potential A, it will simply be along the AZ, because the current density is along the AZ. And we said before that if there was an AY, we would expect to have also a current density AY, but in this case we don't. We're just going to have the AZ, but this is Cartesian coordinate system. Once we have the A, we can use this equation 3.2a, which is shown on the right side of the slide. Then we can insert the A to find also the electric field. Or we can use this equation at the bottom where the curl of H is equal to the current density J plus J omega permittivity times EA. Now, it is good. So these equations, they are in Cartesian coordinate system. But since we want to see also how this antenna or infinitesimally small dipole antenna, how the electric fields and the magnetic fields are in the far field regime, it is easier for us to analyze this problem in spherical coordinate system. So what we want to do, we want to transform from rectangular coordinate system to a spherical coordinate system. And to do that, we just have to look for what is the projection of AZ onto AR, and what is the projection of AZ onto the A theta, and so on. So for this conversion, we just use this this matrix, rotational matrix T. So this is T is a rotational matrix in three-dimensional coordinate system. Now the A, it was initially, this was AZ as given in here, but the projection of A now, if we represent also what is the AR and A theta from AZ, this is what we obtain. So AR, it is AZ cosine theta, A theta is equal to minus AZ sine theta, and those expressions for A, they are just modified by a cosine and the sine. Now, if we have the A, so given A, we can then try to calculate the curl of A in spherical coordinate system. And the del operator in spherical coordinate system, it should include a derivative with respect to r and another derivative with respect to theta. The derivative with respect to phi, it is going to be equal to 0 because the geometry of a dipole, which stands like this, we said before, it doesn't mean anything whether we are to the right or to the left of the dipole, it has this symmetry, or in the front or the back of the dipole antenna. So for that reason, that means that we are not distinguishing between the angle phi. This is also expected only by intuition. That's why in this curl operator, the curl operator, which is a del operator cross product with the vector A, we don't see the derivative with respect to phi at all, but we can also see that A, it had the component along the AR, A theta, A phi is 0, so it looks like now we can find what is HR, A theta, H phi. So this is what we get here. Now, one thing that we can notice here, or that we can have a look at this stage, is that when we see this expression, which is the component of the H field, which is pointing in the phi direction, and actually it has to look in the phi direction because we know that whenever we calculate the curl of a specific vector, we are going to find a result which is perpendicular to the original vector. In the same way that when you take the cross product between two vectors, the result is going to be perpendicular to these initial vectors. So the H, first of all, we can remove some doubts of why the projection of H is only along the angle phi. That's one thing. And another element which is will become useful when we analyze the near field or the far field region is comparing how, looking carefully at this expression which is here in parentheses. So here we have in the parentheses 1 plus 1 over jkr, where j is the square root of -1, so that's a complex number, divided by kr. Now kr is it's a unit which can be used to determine whether we are too far from the antenna or very far, very near. Because we have to include both of these two components, because the k, it can have a wide range of values, because k is equal to 2 pi over lambda. So let's not forget this. K, the propagation vector. This is going to be 2 pi over lambda. And we know that for communication, we can use a huge range which can change several orders of magnitude between 1 megahertz to 10 gigahertz or 20 gigahertz. That means that lambda also is going to change a lot. That's why when we analyze whether we are in the near field or the far field region, we have to look for the Kr value. And there are some cases where the magnitude of 1 actually is just 1, and the magnitude of 1 over jkr, they can be equal to each other. Or so when they are equal, we can conclude something, or we can use a certain, or we can predict how much the different components of the fields are generated, how large they are, how we can approximate them, how we can calculate them. So that's one thing that we have to be careful about. If we are very in the near field, very, very near, then we can say that the complex part is going to be much larger than the real part when we're looking in this expression. But if you are in the far field, so let me correct, because I might have said this wrong. When Kr in this denominator is huge, that means that the real part is much larger than the complex part. Yeah, that's the correct way to say it. So let's move ahead. So this was the H, and now similarly from the H, from A, we found the H. Using these expressions here in this board, we can also find the E, the electric field. And if you remember, when you have done the waveguides, for every waveguide, we used to find all 3 components of the electric field and all 3 components of the magnetic field intensity. Also for antenna, we need to find 3 components of magnetic field intensity and the 3 components for the electric field. The 3 for magnetic field, they were shown, wait a second. Or maybe they're not shown. Oh, yeah, here there are 3 components for the magnetic field intensity. Only 2 of them are 0. The HR, the projection along the H and along the theta, they are 0. So here we have 3 H. Here we have 3 electric field intensities. That's all we need. Now here we can still have another analysis here regarding the behavior of the electric field intensity in different regimes from the antenna, which would be near field, far field. We can still notice here, for example, if Kr is equal to 1, imagine what is Kr equal to 1? K, it's equal to 2 pi over lambda, and R, it can be lambda over 2. So Kr equal to 1, it's really a region where, for example, if you look here for E theta, the magnitude of the 3 terms that you can see inside the parentheses, they will be all equivalent, the magnitudes, right? Because the phase can be different, because we have 1 over j in the second term, but the third term, it will be a pure 1, okay? So, but the magnitude will be comparable. That means that whenever K is this value, whenever R is equal to the half of the wavelength, this is this region where certain values for the electric field and the magnetic field can be found. So this is equal to 1 or approximately 1. No, wait a second. This is lambda over 2 pi. Sorry, this is lambda over 2 pi. Yes. I don't want to confuse you, but this is equivalent to as if the lambda is a full circle, is the perimeter of this one, okay, and the R would be at the radius. But this is just equivalent principle. It's not what it really means. Anyway, okay, so these are, as we said, this would be the E components for the infinitesimally small dipole. Again, this is ER, E theta. Okay, so these are, again, this expression we saw here in the previous 2 slides. They're put here in one slide, where we see the 3 components are equal to 0, and 3 components that are different from 0. 1 electric field is 0, 2 magnetic 0, the rest. So these are all that we may need. Now, if we, for this infinitesimally small, infinitesimal dipole antenna, once we find the fields, we have to also to calculate the power density and the different relevant quantities, which we describe them as E cross the power density, which is measured in watt per meter square, is equal to E cross complex conjugate of H. And E, if we look at this slide here, E, it has a component along the ER and E theta. That's why we see it here. And the H, it has only a component along the H phi. So that's what we need to have here. And let's see what we have here. For a lossless antenna, real part of input impedance is the radiation resistance. Okay. Let's move again. So this is the, again, we have power, and so this is the power density that we have to calculate, and the total power which is generated from an antenna, it should be equal to the power densities which are described in the third equation here in this slide, and integrating over a closed area or closed sphere with a radius r. We have to integrate over surface area, because the unit of power density is watt per meter square, and now it is more reasonable to integrate over a unit which is r squared sine theta d phi. Now, we also notice that since we are integrating over a closed area, the vector which denotes the area vector, it is pointing along the AR. If this is AR, that means that the dot product of AR with A theta is equal to 0, which means that the power density theta does not contribute to the integral of the power. Okay. And now it does not contribute, but then this power, this in fact is purely imaginary, and this one, in fact, this contributes only to the reactive power. Now, the reactive power density, which is, I'm just reading from the slide here, which is the most dominant for small values of Kr, has both radial and transverse components. It does not change between outward and inward directions to form it changes very little, actually, between inward and outward directions to form a standing wave at a rate of twice per cycle. It also moves in the transverse direction as suggested by the equation that we saw above. Now, I just found this interesting. I took this paragraph from a nice paper which was published in 2015. It just reports that, I can simply read this one. You can also read this. So it just reports that the reactive energy. So in fact, we have the radiating energy emitted from an antenna, and we have also the reactive energy. The reactive energy is this one, which is this complex part, which is coming because of the W theta, okay, the power density in the direction of theta. Now, this one, this reactive one, it is stored very in the proximity of the antenna itself, okay? But research has shown that this reactive energy, of course, it's not relevant with regard to a receiving antenna, which can be located very far away from the transmitting antenna. So let's imagine we have a transmitting antenna and the receiving antenna is very far away, and when we receive, it doesn't matter. So the reactive energy, which is very close to this antenna, is in the proximity here. It does not have a direct effect, okay? And we're just saying direct effect. But indirectly, this reactive energy, which is stored very close to the transmitting antenna, to the antenna which is sending the signal, this has an effect for this antenna itself regarding the quality of the signal which is produced and some other parameters. So if we read from here, we notice that while the conventional operation of an antenna concerns radiation, The non-radiating energy stored in its vicinity is a quantity whose behavior determines all aspects of the device functionality. It has been illustrated how reactive energy can affect the signals outside the near field regions. So apparently there is an effect. It is advocated that the radio waves interact and combine with each other all the time, generating near fields even arbitrarily far away from the transmitters that create them and the receivers that detect them. Furthermore, reactive energy can influence the localization of the electromagnetic power concentration in a transient electromagnetic system. So actually this is again something like regarding the W theta component. Apparently it's purely imaginary. It varies as for small kr as 1 over r to the power 5. In fact, let's go back and have a look at the, yes. Yeah, for example, in this expression, we can see what the projection of the power density along the theta direction is. We can see that it is in the, let me think for a moment. In the near field regime, the W theta, it changes as 1 over r squared, r to the power 5, right? Because if kr is very small, that means that 1 plus 1 over kr squared is equal to 1 over kr squared, because it's so large, it's where 1 is negligible, then we would have a dependency of 1 over r to the power 5. But in the far field regime, 1 over kr squared would be so small that the power density W theta, it will change as 1 over r cubed. So when it is close, the gradient of change, it's huge. If we are far away, the gradient of change is smaller. So if you are close, it's 1 over r to the power 5. Far is 1 over r to the power 3. So, okay, so we're seeing here that the power density is primarily imaginary, pulsates back and forth, and it is basically trapped inside the radiant sphere. Okay, so there is an energy which pulsates very close to the antenna. It's also a very interesting effect. A small amount of real power density escapes, leaks out of the radiant sphere, yes, and it is represented by the real part of omega r, which varies as 1 over r squared. This eventually leads to the real power radiated and found in the far field. Okay. The reactive portion is dictated by the capacitance and inductance of the antenna and exists predominantly in the near field. So in fact, this reactive portion is not the same thing, but it is close to equivalent, and it might be worth just comparing these two cases. So the energies, they always oscillate in an AC circuit if we have a capacitor, or they also oscillate whenever we have an AC circuit or AC power supplier which is connected to an inductance. So we have an oscillation of power in these components. Now, something similar is also happening with the reactive energy in the proximity of an antenna. Okay, so it kind of pulsates in and out. Now, here we see the magnitude of the variation of the power density as a function of the radial distance of field terms radiated by the infinitesimal dipole. Now, if we look in this graph, we can see that we have 3 components that we can add together, and these 3 components that we can add together, there is a constant term. Okay, there is also a couple of terms which, as a function of the r, where r is expressed as a function of the wavelength. Let me see if I have something here. No. Okay. So this graph, it's good for you to analyze looking at the same time with these expressions. So for example, here, the power density, we have here 1 plus 1 over kr squared. And here we have, for example, this E theta. E theta, it is composed of 3 terms. One that changes as is just a constant term. This is, I think it's easy for me to go from slide 14 to 21 like this. So that one is shown here. It's a constant term. Then we have 1 over kr. So logarithmic scale of 1 over kr, it is r to the power minus 1. Okay, and the logarithm of 1 over kr squared, the logarithm of this one is 2. Okay, so if we go here, we notice that we have just give me 1 second. Sorry. Hello. Përshëndetje po. Shumë mirë, shikojmë në leksion, a ke ardhe po? Po mirë, hajde këtu të kërkoj Arbani, që janë në leksion. Do kërko Arbani. Okej, po. Do të marrë telefon pas 5 minuta, se janë... Okay. Sorry about this. Okay, so as we can all deduce together that in this graph we see a slope, a line which has a slope of -1, because we can observe here on the y-axis we see 2, and here we see another 2. So apparently it's to the power -1, and we see also another slope, which is actually the third factor that we see in the components for the electric field and the magnetic field. And we notice that all of these terms, they are equal to 1, right, when the ratio of when the spatial relationship between the r and the wavelength, I believe this should be equal to 1. 10 to the power -1, this is 1, 2, 3, 1, 2, 3, yeah. Or maybe not exactly 1, let me think for a moment. So, no, not 1. Then it should be, let me correct myself. So Kr is equal to 1 only when R is equal to lambda over 2 pi. So this means that when lambda is equal to, when R, lambda divided by 6. Okay, so then how we can denote this one? 1 over 6, this is 0.15, or whatever this is, 0.17 lambda. Okay, so I believe, yeah. So this might be one reason that this is not r equal to lambda. It's a different factor. That's why the x-axis is in logarithmic scale. So we can try to read these, and probably we convince ourselves that we're saying something the truth. Or okay, actually I can see it also at the. It's very, very dimly written here that 1 divided by kr squared, this is equal to lambda divided by 2 pi r squared. Yes, that's true. So it's just substituting for k, which is 2 pi over lambda, and the r, it just stands in there. Okay, we can move again. And by the way, we are close to the end of today's session. Do you have any question? So the rest from now on, you can. I'm going to share the slides. You can also go over these, or you can read from the book. But the rest is simply, okay, it's actually the integral of these power densities over a closed sphere. This is what we observe. So we notice that we have radiated power and the complex power, which we call this one the time average reactive power in radial direction. And then the answer will be as shown in here. So the radiated power is in fact expression 4.15, except for the complex part. So we use just the first term in the parentheses. This is again the radiated power, okay. And the reactive one, we also notice that this one, so oh, this is okay. So this is an essential aspect that we should take note, is that the radiated power, it remains constant as the R increases, and the other imaginary power, which is the reactive one, it decreases very fast with R. It's changing as 1 over R to the power 3. And the radiation power is expressed with these terms here. Once we put together some terms, we can also define a radiation resistance of an antenna. And the radiation resistance of an infinitesimally small antenna apparently is proportional to the length square divided by the wavelength square. This is the radiation resistance. And here we can have an example which says that given given the length, find the radiation resistance for an infinitesimally dipole antenna if the length is lambda over 50. So for lambda over 50, we see that the radiation resistance, it's going to be 0.3 ohm. Now here we have this discussion that we mentioned before in the beginning of this session, where we said that since most of the transmission lines, they have impedances in the order of 50 to 75, an infinitesimally small dipole given at this length scale, which is 150 times the wavelength, will result in a resistance of 0.3 ohm. But it looks like it's going to have a huge mismatch between the 50 ohms and the 0.3 ohms, which means that we're going to have a very small efficiency. Now, so the rest of the slides is just analyzes what happens in the near field. Near field, it would be very close to the antenna, Kr much smaller than 1. The equations can be approximated as shown here. On the right, on the left side, there are the expressions that are not approximated. On the left side, there are approximations. This is the near field. We have also an intermediate field. Intermediate field, which is not far field, but is just beyond specific length scale. And in that regime, the expressions for the electric field, they are shown here on the left. And we just put them in the same slide so that you can compare actually what goes on with here. And we can see that, or you can notice what is the difference between the electric field components and the magnetic field. In the near field, only when Kr is larger than 1, and also in the far field where Kr is much larger than 1. Okay, so these were the non-approximated terms, but once we are in the far field, everything, it is, so actually far field, 1 over Kr squared, it will converge to 0 pretty soon. So that means that E theta will be modified accordingly. So it looks like even the only, this is E theta. The E theta, it has also a complex term. Okay, in the far field, I think we can come to an end for today's session. In the far field, once we have the E theta and H phi, we can define the wave impedance, which is going to be given by these components, which most of the time we might expect for this wave impedance to be the impedance of vacuum, if the wave is propagating in vacuum. Do you have any question for what we did so far? If not,